Let's take a second and look at this rare view inside the head of a gamma camera. This is the equipment we use in planar imaging, but we don't usually get to pull back the plastic housing like this. As I rotate the head, you can see the front surface where gamma photons enter the camera. On the other side, the gamma photons hit scintillator crystal made of sodium iodide. This is the layer that converts gamma photons into visible light. Just to prove that to you, we brought in a vial with 300 millicuries of pertechnetate from our molybdenum technetium generator and exposed the camera head to the vial with the light turned off. You can actually see the awesome purple light that comes off the scintillator crystal with your naked eye. This is the photomultiplier tube, or PMT, that we use to detect this visible light. A photocathode at the front of this device converts visible light into electrons, and the machinery inside the tube amplifies those electrons into an electrical pulse. The pulse is tall and wide in proportion to the energy of the incoming gamma photon. What's so cool about the scintillator combined with the PMT is that you're not only detecting gamma photons, but you're also figuring out the energy of each gamma photon that you detect. As you can see, the PMT fits nicely into this plastic black bracket that defines a grid of positions for PMTs. When a PMT breaks, you'll see photopenia in a circular distribution that matches the footprint of this PMT. When the scintillator crystal cracks, the cracks can actually extend across multiple PMT zones based on the size of the crystal that was grown.